Operational Quantum Gravity Spoken Companion to OQG Manuscript Version Econ.5, August 16, 2026, Todd J. Desiato. Chapter 1. What are clocks and rulers made of? General relativity works. Nothing in this presentation is an argument that it does not. The question I want to ask is more specific. When a clock runs slower in a gravitational field, what exactly has changed? When a ruler, an atomic transition, a matter wave, or a physical trajectory differs from the same kind of system somewhere else, are we required to say that space-time itself is the microscopic substance that changed? Or could geometry be the macroscopic record of a deeper change in the quantum matter, from which every clock, ruler, detector, and measuring standard is built? That is the starting point of operational quantum gravity, or OQG. The word operational is important. We never observe a metric directly. We infer geometry by comparing physical things. Clocks compare rates. Rulers and light signals compare lengths. Quantum phases compare actions. Freely moving bodies define trajectories. Every one of those standards is made of matter. General relativity packages all of those comparisons into a geometrical object called the metric. That description is extraordinarily successful. OQG keeps that success. It asks whether the metric has to be fundamental at the microscopic level or whether it can emerge from a universal response of matter. The distinction is not merely philosophical. If geometry is fundamental, then quantum gravity begins by quantizing geometry or by replacing geometry with some more fundamental geometrical object. If geometry is emergent, then the more natural microscopic question is different. We should ask what quantum matter is doing that causes clocks, rulers, energies, phases, and trajectories to scale in exactly the way that general relativity describes. That reverses the usual causal order. The conventional shorthand says that matter tells space-time how to curve, and space-time tells matter how to move. OQG asks whether the deeper order can instead be matter acting on matter through a universal quantum response, while geometry records the resulting comparisons. This is why the paper begins with the complete interacting standard model, rather than with a new microscopic gravitational field. The goal is ambitious, but the claim is deliberately constrained. OQG is not presented as a proof that space-time does not exist. It is not a claim that general relativity is wrong. It is not permission to discard the metric in the macroscopic regime, where the metric is the right description. The claim is that a coherent matter-first construction can be assembled from known ingredients in quantum field theory, causal response theory, induced gravity, composite gravity, and WT-diff gravity. In that construction, the metric is removed from the microscopic causal ordering. A massless spin-2 response reappears in the long wavelength limit. The strength of that response is interpreted as a constitutive stiffness of quantum matter, and Einstein-equivalent gravity is reconstructed at macroscopic scales. If this is correct, Newton's constant is not a primitive stiffness of empty spacetime. It is the reciprocal macroscopic compliance of a collective quantum matter response. That is the central change in interpretation. The paper then goes further. The same causal response that supplies the low-frequency gravitational stiffness also contains damping and absorption at finite frequency. That allows the theory to define a physical ultraviolet boundary through critical damping rather than through an arbitrary cutoff. OQG then makes a specific constitutive identification at that boundary, which produces a dimensionless closure equal to 1/8 pi. And at the simplest one-loop standard model level, That closure makes a concrete prediction for the non-minimal Higgs curvature coupling. Those are large claims, so the theory must also say clearly how it can fail. It does. The complete standard model realization must actually produce the required tensor response, the critical state, the constitutive stiffness, universality, causal stability, and the reconstructed Einstein limit. If it does not, the microscopic realization fails. So this presentation is not an attempt to make the equations sound mysterious. It is an attempt to explain what each layer of the construction is doing. We begin with matter because every experiment begins with matter. Chapter 2. The complete standard model is the source. The first technical decision in OQG is also one of the most important. Gravity cannot be sourced by only electromagnetism, only the electromagnetic vacuum, only quarks, only the Higgs field, or only some special oscillator model. If gravity is universal, the microscopic source has to be universal. The natural object already exists. It is the complete energy-momentum tensor of the interacting standard model. That tensor contains the gauge fields, the Higgs field, the chiral fermions, their Yukawa interactions, energy density, momentum density, pressure, shear, and anisotropic stress. In other words, it contains the physical stress and energy information carried by all of ordinary quantum matter. The first equations in the paper formalize that statement. They do not invent a new gravitational substance. They say that the standard model has one total conserved stress tensor, and that this total tensor is the object whose response we will study. Why is conservation so important? Because a universal long-range gravitational response cannot be assembled consistently from arbitrary pieces that exchange energy and momentum without keeping track of those exchanges. The gauge sector talks to the Higgs sector. Fermions interact with gauge fields and with the Higgs field. Energy and momentum move among all of them. A complete theory, therefore, has to use the completed interacting stress tensor, not separate gravitational constants for separate microscopic components. The next step is to ask how this total stress responds. In ordinary engineering, if I want to know the properties of a material, I perturb it and measure its response. I might apply an electric field and measure polarization. I might apply a magnetic field and measure magnetization. I might apply force and measure displacement. Quantum field theory has the same logic, but the response object is a correlation function. OQG uses a causal, retarded stress response function. Retarded simply means that the response follows the disturbance rather than anticipating it. Cause comes before effect. To calculate that correctly in quantum theory, the paper uses a closed time path construction. One can think of it as a formal way to keep the forward and backward histories needed to describe real-time expectation values and causal response. The important point for this presentation is not the contour mathematics. The important point is that the resulting response function is the one appropriate to physical dynamics. The response contains two kinds of information that engineers already know how to separate. Part is reactive or dispersive. It describes the reversible part of the response, shifts in phase, stiffness, resonance frequency, or stored energy. The other part is absorptive. It describes damping, line width, heating, radiation, decoherence, or other channels in which coherent energy is lost into additional degrees of freedom. Causality connects these two parts. They are not independent knobs. This is a major bridge between the earlier damping intuition and the mature OQG theory. In the older engineering model, gravitational scaling was represented with a damped quantum oscillator. That was too narrow to be a universal theory because real matter contains far more than one electromagnetic oscillator. But the physical intuition survives in a stronger form. The causal quantum response always has both a reactive face and an absorptive face. The low-frequency gravitational stiffness can therefore be the zero-frequency reactive projection of the same microscopic response that contains damping at other frequencies. This does not mean gravity is ordinary friction. It means damping and stiffness are two measurable aspects of one causal system. The paper also includes the symmetric fluctuation kernel. Near equilibrium, fluctuation-dissipation relations connect the noise spectrum to the absorptive response. Again, this is familiar engineering physics in a quantum setting. A system that can dissipate also fluctuates. At this stage, OQG has not yet produced geometry. It has done something more basic. It has identified one realistic microscopic source and one causal response structure. That matters because it avoids a common failure mode in alternative gravity models, starting with a convenient source that cannot actually account for all forms of matter. OQG instead starts with the thing that every successful microscopic theory of ordinary matter already has to contain: the complete interacting standard model. The remaining question is how a geometrical response can emerge from it without putting a fundamental metric back in by hand, Chapter 3. Matter changes first. Geometry follows. This is the conceptual center of the paper. If the metric is not supposed to be a fundamental microscopic dynamical field, then we have to be careful about how it appears in the calculation. The standard model is normally written with a metric or a Vielbein, so that we can define distances, spinors, covariant derivatives, and the energy-momentum tensor. OQG does not deny that mathematical requirement. Instead, it changes the role of the geometrical variable. At the microscopic stage, geometry is used as a source or probe coordinate. We vary that source to ask how the standard model responds. We do not set the metric variation equal to 0 and impose a new gravitational equation on ordinary matter. That distinction is essential. The paper keeps the two closed time path source branches separate long enough to compute the real causal response. Then it performs a Legendre transform. A Legendre transform sounds more intimidating than it is. In engineering and thermodynamics, we often change which conjugate variable we treat as the independent one. We can describe a capacitor using voltage or charge. We can describe a mechanical system using displacement or force. The information is the same, but the useful representation changes. Here, the calculation changes from a functional written in terms of a geometrical source to a functional written in terms of matter stress. Once that change of variables is made, the key causal chain becomes very simple to say. Matter changes. The total stress changes. The inverse causal susceptibility tells us what collective geometrical response corresponds to that change. That is the physical meaning of several equations in Section 3. The geometry is no longer the first actor. It is the conjugate collective response reconstructed from how quantum matter reacts. The inverse is important. If a susceptibility tells us how stress changes when the geometrical source is changed, then the inverse susceptibility tells us how the collective geometrical variable changes when the matter stress is changed. That inverse response also produces a long-range matter-to-matter interaction. Fundamental graviton has not been inserted into the microscopic action. Instead, the long-range spin-2 interaction appears through the inverse collective stress response kernel. This is where OQG connects with metric-independent composite gravity research. Those models provide examples in which matter variables can support an emergent spin-2 interaction after an auxiliary geometrical object is removed. OQG does not claim those earlier models are the standard model. It uses them as proof that the logical route is possible. Only after the geometrical source has been eliminated from the microscopic description does OQG reconstruct the operational tensor used for macroscopic physics. This ordering also matters for the Weinberg-Witten theorem. The theorem places strong restrictions on composite massless particles in a fundamental Lorentz covariant theory with a particular kind of non-zero, conserved total energy-momentum tensor. Metric-independent composite gravity models evade the relevant hypothesis, because the fundamental formulation does not contain the forbidden total stress in the required form, even though an emergent matter stress exists in the low-energy phase and couples to the emergent spin-2 field. OQG adopts that ordering. The structural route is therefore clear. Eliminate the source geometry first, then interpret the long-range collective tensor as emergent geometry. The paper is careful not to overstate this. The matter stress reduction and the no-go evasion route are already defined structurally, but the full chiral standard model still has to be evaluated far enough to verify the corresponding no-ether identity and WT-diff Ward structure. The remaining issue is realization, not a new escape mechanism. There is another consequence of the matter-first construction. An arbitrary homogeneous shift in the zero of the quantum stress does not change the connected causal response. If I add the same constant vacuum offset everywhere, proportional to the metric, that constant does not appear in the fluctuations of the stress around its mean, and it does not change the connected commutator that defines the response. This is what the paper calls vacuum shift blindness. It does not mean that all vacuum physics disappears. Casimir stresses remain physical. Vacuum polarization remains physical. Phase transitions remain physical boundaries, remain physical. Pressure differences, gradients, excitations, and connected vacuum fluctuations remain physical. What disappears from the local source information is only the arbitrary homogeneous additive baseline. That distinction becomes important later when we reconstruct the macroscopic Einstein equation. The paper also keeps a first-order spin-current sector because fermions have intrinsic spin. The stress response is the long-range symmetric tensor channel that fixes ordinary gravity, but mixed stress-spin response can still contribute to finite frequency, contact, and short-distance behavior. So by the end of Section 3, the causal order is established. Standard model matter is primary. Geometry is reconstructed from the response. The next task is to show why that reconstructed response has the correct long-range tensor structure, Chapter 4. WT-diff and the two physical tensor modes once the matter-only reduction is complete. OQG reconstructs an operational tensor to describe the long-wavelength gravitational response. This is where WT-diff enters. WT-diff is short for Weyl transverse diffeomorphism symmetry. The name is less important than the physical job it performs. A general symmetric tensor contains more components than a massless gravitational field is allowed to propagate. Some components are coordinate redundancy. Some correspond to an overall local scale or volume degree of freedom. The physical radiative gravitational field has only two independent helicities. Those are the familiar plus and cross tensor polarizations. If a ring of freely falling test particles is hit by a plus-polarized gravitational wave, one transverse direction stretches while the perpendicular direction shrinks. Half a cycle later, the pattern reverses. The cross-polarization produces the same kind of shear pattern rotated by 45 degrees. The important word is shear. The physical wave is not an independent scalar breathing of local volume. In the OQG construction, the determinant normalized operational tensor is unchanged under a local rescaling of the source representative. That means the overall Weyl scale is redundant in the emergent representation. After linearization in a local tangent frame, WT-diff symmetry protects the massless tensor structure and forbids an ordinary algebraic mass term. The resulting long-range pole has the two transverse traceless helicities required by ordinary gravitational waves. The use of a local Lorentz frame here does not mean the theory has secretly returned to a fundamental global Minkowski background. Every curved spacetime theory uses infinitesimal local inertial frames to describe local physics and spinors. OQG uses the local Lorentz metric in exactly that sense, as the tangent space representation of the emergent geometry. The paper's Figure 1 summarizes the ordering. First comes the complete standard model matter response. Next comes the matter-only reduction. Then comes the emergent tensor with WT-diff redundancy. Only after that do we define the transverse traceless constitutive stiffness and the critical damping boundary. Then comes scale covariant critical closure. Finally, at long wavelengths, the construction reduces to Einstein-equivalent dynamics. That figure is worth remembering because the order prevents several conceptual confusions. WT-diff does not calculate Newton's constant. Symmetry tells us what kind of long-range field can exist. It protects the massless two-helicity structure, but symmetry does not tell us how stiff that field is. That numerical strength must come from the dynamics of the quantum matter response itself. Likewise, vacuum shift blindness is not a second theory of gravity. Spin current completeness is not a second gravitational sector. They are constraints and additional response channels inside the same matter system. So by this stage, the theory has answered one question. Why should the long-range collective response look like gravity rather than like a random scalar or vector field? Because the reconstructed fixed-measure WT-diff representation leaves the correct massless spin-2 sector. But another question remains. Why is gravity as weak as it is? What determines the value we call Newton's constant? That takes us from symmetry to constitutive physics, Chapter 5. Gravity as a constitutive stiffness of quantum matter. The paper now makes one of its most important reinterpretations. In a material, stiffness tells us how much source effort is required to produce a response. Compliance is the inverse. A stiff system responds only a little to a given source. A compliant system responds more. OQG applies that language to the physical transverse traceless quantum stress response. At very low momentum, the slope of the transverse traceless susceptibility defines a two-derivative constitutive stiffness. When the units are restored, the same coefficient is related to Newton's constant. The relationship says, physically, that Newton's constant is the reciprocal macroscopic compliance associated with that matter stiffness. This reverses the usual interpretation. Instead of saying that G is a primitive coupling constant belonging to spacetime, OQG says that the quantum matter system has an enormous transverse traceless stiffness, and the small gravitational coupling we observe is the macroscopic compliance of that stiff response. A large stiffness means a small g. A smaller stiffness would mean a larger gravitational compliance. This is an engineering statement about the response, not merely a change of notation. The stiffness can also be written spectrally. A spectral representation separates contributions from resolved modes, overdamped response, and local contact structure. The details matter for a full quantum field theory calculation, but the basic picture is straightforward. If matter has physical states that can absorb or respond in the tensor channel, those states contribute to the causal response. The imaginary or absorptive part tells us about real dissipation and spectral weight. Through dispersion relations, that same spectral structure contributes to the real or reactive stiffness. So once again, damping and stiffness are two faces of one causal kernel. This is where the older oscillator intuition reappears in a form that can apply to the complete standard model. The next question is what happens as we move to higher and higher characteristic energy. An effective low-energy theory can always be written as a derivative expansion. At very long wavelengths, the two-derivative Einstein-like term dominates. At shorter wavelengths, higher derivative terms become more important. Eventually, a truncated local series must fail. Normally, that creates an ultraviolet question. Where does the effective theory stop? Is there a cutoff? Is that cutoff fundamental? Is it imposed by hand? OQG proposes a physical answer. The same causal matter response that generates the infrared stiffness also contains a transition in its pole structure. To understand that, think of an ordinary damped oscillator. With low damping, the oscillator rings. Its poles have a real oscillation frequency and a negative imaginary part describing decay. As the damping increases, the oscillation frequency falls. At critical damping, the two oscillatory poles merge on the negative imaginary axis. Beyond that point, the response is no longer an oscillation. It becomes purely relaxational. The mature OQG theory does not define the ultraviolet boundary using the simple oscillator formula. The actual defining condition is a double zero of the full non-Markovian inverse retarded spin 2 response. But the oscillator gives a clean physical interpretation of what that double zero means. At the critical point, the coherent real frequency vanishes. The paper defines a dimensionless pole loading, so that this critical state has loading equal to 1. That gives OQG a dynamical boundary instead of an externally imposed energy cutoff. Below the boundary, coherent tensor modes exist. At the boundary, the coherent pole pair merges. Beyond it, the response is overdamped or relaxational. This also changes how we interpret the failure of the low-energy curvature expansion. When the derivative expansion stops converging near the critical state, that is not the theory becoming physically meaningless. It is the approximation telling us to stop using the truncated local series and return to the complete causal kernel. The underlying response remains finite and causal. That is an important conceptual distinction. The ultraviolet problem becomes a problem in the dynamics of quantum matter, not a request for an immutable ruler placed outside the theory. But now a new question appears. If the critical state is physical, how do we compare its microscopic scale with gravity without secretly importing an absolute Planck scale? That is the purpose of operational scale covariance, Chapter 6. No external ruler. Scale covariance and critical closure. This section is easy to misunderstand, so I want to state the idea carefully. OQG is not claiming that changing units changes physics. A passive change from meters to feet is meaningless. Nothing physical has happened. The theory is talking about comparisons between different physical states in which all matter-built standards participate. Imagine that a complete physical state changes in a way that changes its characteristic energy scale. The clocks in that state are made from matter. The rulers are made from matter. Mass standards, transition frequencies, correlation lengths, the Higgs scale, QCD scales, and the effective gravitational compliance all belong to the same physical state. OQG, therefore, refuses to hold one-dimensional object outside the system and declare that object to be the absolute ruler against which every state must be judged. In particular, the Planck scale is not exempt. If the matter standards co-scale, then a Planck energy or Planck length constructed from the local values of the constants co-scales as well. What remains physically meaningful are invariant combinations and dimensionless ratios. This is why the critical correlation energy in OQG is finite but not absolute. Call it the critical correlation energy. It labels the state at which the coherent spin-2 response reaches the non-Markovian pole merger. If the microscopic spectrum changes, the critical state can move. The stiffness moves with it. The corresponding macroscopic gravitational compliance moves with it. There is no fixed ultraviolet marker nailed outside the system. The paper then makes its central new physical identification. The critical state has two independently defined properties. Microscopically, the causal matter response gives it a correlation length. Macroscopically, because the settled long wavelength theory is Einstein equivalent, the same localized energy state has an asymptotic gravitational radius read from its far-field 1/r behavior. The key word is asymptotic. The paper is not using the Schwarzschild metric as the microscopic field equation at the critical length. It is using the Einstein equivalent far field to define the gravitational radius of the state. Separately, the microscopic causal response defines the correlation length of that same state. OQG then identifies the dimensionless gravitational self-loading formed from those two scales with the unit dynamical loading reached at critical damping. That is the critical constitutive identification. It is a new physical principle of OQG. It is not derived from general relativity alone. It is not a fitted normalization. It is not the result of choosing a convenient Planck cutoff. It is the statement that the critical dynamical loading of the quantum matter response and the gravitational self-loading of that same physical state are two descriptions of the same dimensionless boundary condition. When the correlation length and the asymptotic gravitational radius meet in this way, and when the gravitational stiffness is written in its Einstein normalized form, the dimensionless constitutive ratio becomes 1/8π. That is the critical closure. The remarkable part is that the dimensional critical energy cancels out of the ratio. The closure is dimensionless. This is why moving the critical energy cannot be used to repair a wrong dimensionless coefficient. The spectrum, the boundary, and the stiffness move together. The paper also asks whether the overdamped branch could later return toward zero frequency and create another long-range gravitational mode. That would be disastrous, because ordinary gravity has one massless long-range tensor sector, not an extra hidden pole. The spectral argument prevents this if the completed stiffness remains finite and positive. A new pole approaching zero with non-zero gravitational residue would create another non-analytic infrared contribution. Local contact terms could not cancel it, and an accumulation of positive tensor spectral weight at zero would make the low-energy moment diverge. So an overdamped mode has only two acceptable possibilities. It remains separated from zero by a finite relaxation scale, or its gravitational residue vanishes sufficiently fast that it decouples. In either case, it does not reappear as a second long-range gravitational degree of freedom. This gives the ultraviolet picture a coherent form. The low-energy Einstein-like response is one limit of the causal quantum matter system. The critical boundary is a dynamical transition in that same system, and the closure is a dimensionless condition internal to the state. Now we can ask a very concrete question. What does the actual standard model say about the size of that dimensionless response? Chapter 7. The 24 pi gap and the Higgs curvature prediction at this point, the theory stops being only structural and produces a numerical target. There is a known one-loop calculation of an induced Einstein term from quantum matter. At the simplest free, sharp boundary level, the minimal standard model gives a dimensionless gravitational response proportional to an effective count of the standard model degrees of freedom. For the minimal standard model without right-handed neutrinos, the scalar, fermion, and gauge field contributions almost cancel. The net count is 1. That produces a one-loop stiffness coefficient equal to the critical energy squared divided by 192 pi squared. OQG's critical closure requires the critical energy squared divided by 8 pi. The ratio between the required OQG coefficient and the minimal free one-loop standard model coefficient is exactly 24 pi. This is where scale covariance becomes decisive. Both coefficients are proportional to the same critical energy squared. So changing the critical energy cannot fix the discrepancy. The missing factor is not a missing energy scale. It is a dimensionless response problem. That is much more informative. Now look at the actual renormalized standard model in curved space-time. The Higgs field is allowed, and in fact required by renormalization, to have a non-minimal coupling to curvature. That coupling is dimensionless, and it changes the scalar contribution to the induced Einstein coefficient. The Higgs doublet contains 4 real scalar degrees of freedom. When their non-minimal curvature coupling is included, the effective scalar contribution changes in a simple way at this approximation order. OQG can therefore ask a direct question. What value of the Higgs curvature coupling would make the one-loop standard model response satisfy the critical 1/8 pi closure? Solving that condition gives a boundary value equal to 1/24 minus pi. Numerically, that is approximately negative 3.0999. This is one of the most concrete predictions in the paper, and it has to be stated with its limitations. It is not a claim that the experimentally measured low-energy Higgs curvature coupling is already known to have that value. It is not a non-perturbative result. It is not the final standard model answer. It is a sharp boundary, minimal standard model, one-loop prediction for the value of the non-minimal Higgs curvature coupling at the critical state. The complete interacting theory can change the result. QCD contributes. Electroweak interactions contribute. The Higgs self-interaction contributes. Fermionic interactions contribute. Ward-required contact terms and the overdamped sector contribute. The paper therefore writes the exact completion as the leading one-loop result plus calculable corrections. The purpose of the one-loop number is not to declare victory. Its purpose is to turn an apparently unexplained factor of about 75 into a specific standard model boundary prediction that can be tested by the completed calculation. That is a much sharper situation. The final microscopic closure problem can now be stated as 2 conditions on one and the same standard model state. First, the exact causal response must develop the critical non-Markovian double zero. Second, the transverse traceless stiffness of that same state must satisfy the 1/8 pi constitutive condition. These are not 2 adjustable scales. They are 2 dimensionless statements about one physical spectrum. If the complete standard model cannot satisfy them simultaneously, the OQG critical closure fails. That is the right standard. A quantum gravity proposal should not be protected from calculation. It should become more vulnerable as it becomes more precise. Chapter 8. How Einstein gravity reappears so far, I have described the microscopic ordering very differently from general relativity. Matter response is primary. Geometry is reconstructed. The gravitational strength is a constitutive coefficient. The ultraviolet boundary is a critical transition in the matter response. Yet at large distances and low frequencies, the theory must still give the same gravity we already know. This is where the construction becomes deliberately conservative. On a settled long wavelength branch, the fixed measure WT diff tensor obeys a traceless local gravitational equation. The complete matter stress is conserved. Geometry satisfies the contracted Bianchi identity. Those two conservation structures are enough to integrate the traceless equation. The result is the full Einstein equation, with a cosmological term appearing as an integration constant. The important point is the causal ordering. OQG does not start by inserting the Einstein-Hilbert action as the microscopic fundamental theory and then reinterpret it. The Einstein equivalent macroscopic equation is reconstructed from the emergent tensor representation, the constitutive coefficient, conservation, and the Bianchi identity. So ordinary Newtonian gravity follows. Gravitational redshift follows. Universal free fall follows, provided the microscopic standard model response produces the required common infrared projection. The massless gravitational wave sector follows from the transverse traceless propagator. The same constitutive coefficient controls both the static and radiative long-range limits. Now return to the vacuum energy question. Because the microscopic connected response is blind to an arbitrary homogeneous shift in the zero of stress, the local traceless macroscopic equation is also unchanged by such a shift. The cosmological integration constant is simply relabeled. This means that an arbitrary homogeneous QFT vacuum baseline is not first promoted to a gigantic local curvature source and then cancelled against a separately chosen bare cosmological constant. The arbitrary zero never enters the local source information in that way. This is the precise sense in which OQG removes the local source form of the traditional vacuum catastrophe. It is equally important to say what this does not accomplish. OQG does not calculate the observed numerical value of the cosmological constant in this paper. It does not make Casimir stresses disappear. It does not remove vacuum polarization. It does not erase physical phase transition energy, boundaries, gradients, fluctuations, or non-uniform vacuum states. Those are state-dependent stresses and remain gravitationally active. Only the arbitrary homogeneous baseline is quotiented out of the local source. This also explains why one cannot take a settled Einstein equivalent equation and simply replace Newton's constant by an arbitrary function of space and time to model an engineered transition. During a real transition between constitutive states, the system is not described only by the settled low-frequency branch. The full non-local causal response carries energy and momentum through memory, spectral response, spin current channels, and contact structure. Conservation remains mandatory. This point matters for any future engineering application. Changing a constitutive state is a dynamical process. There is no free gravitational parameter that can be turned like a dial while ignoring the degrees of freedom that perform the turning. By the end of this section, OQG has returned to the world we already measure. That is intentional. A successful microscopic theory of gravity should not destroy the empirical achievements of general relativity in the regime where general relativity works. The difference is underneath, In GR, geometry is the starting dynamical language. In OQG, Einstein geometry is the long wavelength record of a universal quantum matter response. Chapter 9. What experiments already require because OQG reconstructs Einstein-equivalent dynamics on its settled infrared branch. Many familiar experiments are not expected to distinguish it from general relativity. That is a feature, not an escape. Optical clocks have measured gravitational redshift over remarkably small height differences. Matter wave experiments measure the gravitationally induced quantum phase. Atom interferometers and the microscope satellite place stringent limits on violations of universality of free fall. Gravitational wave observations show a massless radiative sector traveling at the locally measured speed of light to very high precision, with the tensor behavior expected from general relativity. OQG has to satisfy all of those constraints. A different redshift in the ordinary weak field would falsify the proposed Einstein-equivalent infrared branch. A composition-dependent low-energy gravitational coupling outside the known experimental bounds would falsify it. An extra unsuppressed long-range tensor pole would falsify it. A wrong gravitational wave propagation speed would falsify it. A negative or unstable transverse traceless stiffness would falsify it. Failure of the retarded response to remain causal would falsify it. The theory is also specific about vacuum physics. It removes only the arbitrary homogeneous additive stress zero from local source information. If an experiment required that arbitrary zero itself, as opposed to a physical difference or fluctuation, to appear as an independent local gravitational source, that would contradict the construction. Scale covariance also has to be interpreted correctly. It does not say that I can rename units and create gravity. It says that physically different complete states can have different matter standards and different constitutive response, while local observers inside each settled state still measure the usual local invariance. The new content lies in the causal relation between those states. Cosmology is therefore an important unfinished test. A homogeneous cosmological history can sometimes be represented in more than one set of variables. One can describe expansion geometrically, or in some formulations shift part of the description into evolving matter standards. But a change of description does not remove physical history. Any complete OQG cosmology still has to reproduce the observed dimensionless thermal and reaction history of the universe. It must account for primordial nucleosynthesis. It must account for recombination. It must reproduce the cosmic microwave background. It must reproduce structure growth and the observed distance redshift relations. The current paper does not claim to have completed that calculation. Strong field gravity is another open arena. The fact that the infrared equation is Einstein equivalent does not imply that every formal strong field spacetime solution automatically has a valid microscopic matter response history. A physically admissible solution should have a causal preimage in the underlying response. That may become especially important for horizons, singular limits, and chronology-sensitive solutions. So where should we expect genuinely new tests? Not by looking for a small mismatch in ordinary gravity, where OQG is intentionally constructed to reproduce GR. The decisive tests are the explicit standard model realization of mechanisms already derived in the paper. Can the formally defined matter stress Legendre reduction be made explicit for the full chiral standard model? Does that realized functional verify the metric-independent Noether identity and the reconstructed WT-diff-Ward structure? Does its tensor spectrum contain the required critical double zero? Does the stiffness of that same state satisfy the 1/8 pi constitutive condition? Does universality emerge from the complete response rather than being inserted? Does the one-loop Higgs curvature boundary remain consistent after the full interacting corrections? Those are hard tests, but they are exactly the kind a serious microscopic theory should expose itself to Chapter 10. What remains, and the meaning of the theory, the final sections of the paper, are deliberately explicit about what has been constructed and what remains unfinished. The construction now forms one continuous matter-first chain, and it can be stated in one sequence. Complete standard model matter supplies the source and causal response. The geometrical probe is Legendre transformed into stress space and removed from the microscopic ordering. Physical matter changes then generate collective geometry through the inverse retarded susceptibility. Only after that reduction is the fixed measure WT diff tensor reconstructed. The transverse traceless response defines the gravitational stiffness. The same causal kernel defines a critical damping boundary. Scale covariance prevents that boundary from becoming an absolute external ruler. The critical constitutive identification produces the 1/8 pi closure. And in the long wavelength limit, conservation and the Bianchi identity reconstruct Einstein-equivalent gravity. That is the construction developed in the paper. But several calculations still decide whether nature actually realizes it. The first is the full interacting standard model tensor response. The paper uses the complete standard model as the correct microscopic source, but the exact non-perturbative transverse traceless kernel has not been calculated in the form OQG requires. That calculation has to include QCD, electroweak interactions, the Higgs sector, chiral fermions, contact terms, and the overdamped contribution. It has to determine whether the exact critical pole condition and the constitutive closure have one common physical solution. The second major calculation is to evaluate the already defined matter-stress Legendre functional for the full chiral standard model far enough to make its source conjugate response and reduced matter functional explicit. The structural root has independent precedent in composite gravity and stress space constructions. OQG uses that established root. It does not require a new Weinberg-Witten evasion mechanism. The remaining standard model task is to verify the corresponding metric-independent Noether identity and show that the reconstructed infrared response carries the required WT diff Ward structure. The third task is to refine the one-loop Higgs curvature prediction. The value 1/24 minus pi is a leading boundary prediction under stated approximations. The full renormalization group evolution and interacting corrections have to be calculated. The fourth task is universality. Using one total conserved standard model stress is the correct organizational starting point, but exact composition independence cannot simply be declared. It has to emerge within experimental bounds. Then come strong fields and cosmology. Those are not decorative extensions. They are necessary tests of whether the same matter-first causal construction remains viable outside the perturbative regime. This is why I do not describe OQG as a finished theory of everything. The paper proposes a specific microscopic architecture for gravity and reduces the remaining questions to calculations that can, in principle, succeed or fail. That is already a meaningful change from a purely interpretive proposal. The theory says where the gravitational field comes from in the construction. It says what sets its massless tensor structure. It says what sets its strength. It gives a physical meaning to its ultraviolet boundary. It gives a dimensionless closure condition. It produces a concrete one-loop standard model consequence. It recovers Einstein gravity in the infrared. and it states the conditions that would falsify the microscopic realization. The deepest idea remains operational. Every metric we infer is inferred with matter. Every clock is matter. Every ruler is matter. Every detector is matter. Every quantum phase we compare belongs to matter. So perhaps the successful geometry of general relativity is not telling us that geometry must be the ultimate microscopic substance. Perhaps it is telling us that matter responds universally enough, that all of our physical standards agree on one emergent geometrical description. That is the meaning of the phrase I used to summarize operational quantum gravity. Matter tells matter how to scale, while geometry records the comparison. If the complete standard model satisfies those remaining realization tests, that sentence becomes more than an interpretation. It becomes a microscopic statement about why gravitational geometry exists at all.